In this module, we will look at the ideal liquid mixtures. When introducing ideal liquid mixtures, we must first understand the similarities and differences with mixtures of ideal gases. In an ideal gas, as well as in a mixture of ideal gases, molecules do not interact with one another. However, this model isn't suitable for liquids, as atoms and molecules certainly interact in the liquid state. If they didn't, the liquid would simply transform into a gas. Now, for ideal liquid mixtures, while we do have interactions, they are identical. This means the interaction between molecules of component A in pure A is the same as the interaction between molecules of component B in pure B, and it is the same as the interaction between molecules of A and B in the mixture. The key here is the equivalence of interactions, not the absence of them. Unlike the ideal gas, where the mixing process is entropy-driven due to the absence of interactions, in an ideal liquid mixture, mixing is also entropy-driven, but because the interactions between the different molecules in the mixture are of the same strength as those in pure liquids. Such behavior is typically observed in mixtures of chemically similar liquids. We can define an ideal liquid mixture as a mixed phase where the chemical potentials of all components obey the following relation. The chemical potential of component I in the liquid mixture is equal to the chemical potential of that component in pure liquid I plus RT times the natural logarithm of the mole fraction of the component in the mixture. Let's compare this to the chemical potential of I in the gas phase. It can be expressed by this already introduced equation. The chemical potential of every component in the liquid and gas phases are equal to each other, both when the liquid is pure or it is in the mixture. Thus, by equating the chemical potentials of a component in the liquid and gas phases, we obtain this equation. It states that the mole fraction of a component in an ideal mixture, Xi, is equal to the ratio of its vapor pressure in the mixture to its vapor pressure above a pure substance I. This equation is known as Raoult's law for ideal mixtures. Raoult's law was originally deduced as an empirical relationship that describes the vapor pressure of components in a mixture of liquids. It was derived from a series of experiments conducted by François Raoult on mixtures of closely related liquids, like benzene and methylbenzene. We will illustrate Raoult's law for an ideal binary mixture of two components, A and B, in the following figure. Here, the horizontal axis represents the molar fraction of component A, labeled Xa. The vertical axis represents the vapor pressure P. This line represents the vapor pressure of component A, denoted as PA. This line runs from zero pressure when there is no component A to its vapor pressure when it's pure, which is PA star. The second line denotes the vapor pressure of component B, PB. When there is no component A, the component B is in its pure form. The vapor pressure PB starts from its vapor pressure when it's pure, PB star, and decreases linearly to zero when A is pure and B is absent from the mixture. The total pressure of vapors in the gas phase, P tot, is the sum of the individual vapor pressures of A and B at any given composition. When both A and B are present, their respective vapor pressures are directly proportional to their molar fractions. Given that the total pressure is a sum of two linear functions, it is also represented by a line. To summarize, for an ideal binary mixture at constant temperature, the relationship between total vapor pressure and composition is linear. Some binary mixtures with structurally similar components obey Raoult's law throughout the composition range from pure A to pure B and thus form an ideal mixture of solution. However, most liquid mixtures show significant deviations from Raoult's law when considering the whole composition range. Nevertheless, even for these mixtures, Raoult's law tends to become more accurate for the major component as its concentration increases and approaches purity. Thus, Raoult's law acts as a limiting law. Its predictions become increasingly accurate as one of the components become more prevalent in the mixture, approaching purity. In other words, a real solution follows Raoult's law closely the more dilute it becomes. While only some liquid mixtures strictly satisfies Raoult's law, it is helpful to first introduce the thermodynamic model of ideal mixtures and then compare it with the behavior of real systems. In real-world scenarios, combining two volatile and miscible liquids often results in a solution that doesn't obey Raoult's law. When we look at a vapor pressure diagram for a non-ideal liquid mixture, it can differ from what we expect based on Raoult's law. Why is that so? The answer lies in the nature of molecular interactions. In a binary solution of components A and B, the interactions between A and B may differ from the interactions between molecules of A or between molecules of B. For instance, if the vapor pressure is higher than predicted by an ideal behavior, it's called a positive deviation. This is depicted on the left side of the slide. This higher than ideal vapor pressure indicates so-called repulsive interactions between molecules of different liquids in the mixture. It actually means that A-B interactions are weaker compared to AA or BB interactions. Such interactions results in the molecules having a slightly higher chemical potential and being more active compared to an ideal case. A higher chemical potential for a component in the mixture means that its vapor pressure is also higher. On the other hand, when the observed vapor pressure is less than that of an ideal mixture, we term it as a negative deviation, illustrated on the right side of the slide. Negative deviations are caused by A-B interactions that are stronger than AA or BB interactions. These attractive interactions lower the chemical potential and the vapor pressure of components compared to the ideal case.